Hello, this is Varsha Radhakrishnan, and I'm presenting my final project on comparative analysis of performance of Reed-Solomon, low-density parity check, and parallel concatenated convolutional coding across a noisy channel. This is for EEL6509 wireless communication. So we will be covering an overview about the three types of codes that are being compared, that is the Reed-Solomon, LDPC and PCC codes, and doing an in-depth analysis about their encoding and decoding techniques. And finally we'll be studying the comparison of their error performance and plotting the SNR versus BER plot in MATLAB. All simulations are made in MATLAB and the results are studied and conclusions are drawn from them. In today's advanced technology, high-speed data transfer is of great importance, especially when a large number of channels are intermodulated, or channel crossing and intermixing is very common in today's communication media. Wireless is no less, and when data is transmitted across long distances, errorless transmissions are in need for all applications. The Reed-Solomon codes that were invented by Reed and Solomon in the 60s are the systematic linear block codes. It is a block-based error correction code technique, and they find many applications in digital communications and storage. A number of these applications are DVDs, CDs, satellite communications, modems, ADSL, XDSL, etc. In Reed-Solomon encoder, the digital data is added along with redundant bits. Errors occur during transmission or storage for a number of reasons. For example, scratches on a CD or noise or interference. The decoder process takes this signal across each blocks and attempts to recover the signal. The Reed-Solomon codes are a subset of the BCH codes. They are represented by n, k, where the original message is divided into blocks, which is encoded into a number of symbols, n number of symbols. N represents the symbols that were created, that were encoded, and K represents the original message signal. The Reed-Solomon codes are represented by the symbols that are created, and the decoding process, the algebraic decoding procedure, can correct errors and erasures. The architecture for the Reed-Solomon code is based on a specialist area of mathematics known as Galois fields or finite fields. A finite field has a property of arithmetic operations. This gives rise to generator polynomials that are factored in when we are doing our encoding and decoding processes. The LDPC codes are represented using matrices called the H matrix. They are very popular because they approach the channel limit. LDPC codes find a lot of relevance in today's applications. They are a class of linear block codes as well, and their characteristic is the parity check matrix, which contains only a few ones in comparison to zeros. The advantage, as I said, was to provide providing a performance which is very close to the capacity for a lot of different channels, and linear time complex algorithms for decoding. So, uh, so the H matrix is represented for the LDPC codes. The LDPC codes are constructed using these matrices, and the decoding algorithm is so complex because of the feature of LDPC codes to perform near the Shannon limit of a channel that exists for large block lengths. So to put it simply, the performance increases when the block length is increased. This property is exploited when LDPC codes are used in various applications. The PCCC codes are the turbo codes that which are referred to were this first class of turbo codes. They are of more recent class, and they are a high performance forward error correction codes. They they were the first practical codes to closely approach channel capacity, a theoretical maximum for the code rate at which reliable transmission is still possible for a noise level. It finds applications in 3G mobile communications. Turbo codes are close competitors of the LDPC codes for their performance. So we shall go to our simulations in MATLAB and check our error performance. So this is my code for the Reed-Solomon. The message is sent across a channel. It is modulated and an AWGN noise is applied across the channel. When this message is received, it is demodulated, decoded, and the original message is recovered. Meanwhile, we calculate the error, the number of errors. We plot the BER versus the SNR plot. So when you plot the graph, a decent enough graph emerges for the Reed-Solomon codes. Next one is the LDPC codes. The LDPC codes are, the functions are defined first. They are iterated over the same number of bits, bit inputs, the same message input, and as before, an AWGN noise channel, noise is applied across the channel. So the variance and mean is a factor that is created in when the received signal is computed for SNR, and the error statistics are taken. The LDPC variance is estimated, and the plot for BER and SNR is plotted. So sorry, this is our plot for the LDPC codes. This shows better performance over the Reed-Solomon codes for the given SNR values. The SNR values here are quite limited, from 0.2 to 1 dB. We also now examine the PCCC codes. The iterations are the same, the block lengths are the same, and the functions for the encoder, turbo encoder is called. A noise is added and BER is computed after the demodulation and decoding process has happened in the receiver. And this is the graph that we obtained for the PCCC codes. They are of this, the study of BER versus SNR shows the different characteristics of all three of the error correction codes. So these are the plots again. So as I said, the LDPC codes show better performance when compared with the Reed-Solomon codes. The more recently developed PCCC codes show good performance for SNR, but the interesting parameter that we noticed is that at a higher value of SNR, the performance of LDPC is much better, because the PCCC codes approach an effect called flooring, where the value of SNR drops to 0 slower than expected. So this phenomenon called error flooring is the disadvantage found in PCCC, which makes LDPC a much better form of error correction in applications in communication at higher values of SNR. So this is hence we've compared our error, the bit error rate along with versus the SNR, and found a distinct comparison, a distinct difference between each of the three error correction codes. And a future in this can be the analysis of the drop in performance for the turbo code, and due to the error flooring, and improvement in error performance in that area. Thank you.